Hello, my name is Jacob Varley, and this is my presentation on Lab 4 oscillation. So the purpose of the lab was to use a computational model and a tracker to observe and quantify changes in energy in an oscillating system. We found that the oscillation time of the spring is 1.55 seconds, the spring constant is 6.555 newtons per meter, and the relaxed spring length is 0.098 meters. So the fundamental principles we needed were was the momentum principle, Newton's second law, with velocity and position update formulas, force due to gravity, force due to the spring, the basic energy principle, and then how to calculate kinetic, gravitational potential, and spring potential energies. The tracker data shows the movement extremely well, where y decreases as the spring moves downwards and increases as it moves upwards, and the x direction is centered around the spring's starting place. So with the mass of the spring being given as 0.402 kilograms, we can calculate f of g, and the period of oscillation was experimentally determined through tracker to be 1.55 seconds in the x direction. So the spring constant must be 6.555 newtons per meter. Finally, using all of the values, we can determine that the resting length of the spring is 0.098 meters. The initial conditions in the computational model were, again, the mass being 0.402, the initial position given by tracker and velocity, g equals 9.8, the spring constant we found, the initial resting length that we found, and then all of these equations to update the energies, total energy, change in energy, and energy in each subsection of the system given other variables. So to look at the entirety of the while loop, we have all of our energies identified with variables, and then we have F grav calculated, and then the force due to the spring calculated, and then F net being the addition of them two. We have velocity and position update formulas, and then finally we have energy update formulas where it looks at the change in energy as a total and the way and updating new energies for all of the different subsections. So in our results, we can see that the potential energy due to gravity is almost perfectly opposite to the potential energy due to the spring, and that the change in total energy is always zero. So there's no energy lost or gained in the entirety of this system. With these graphs, we can see that the experimental and computational model of the system are extremely similar, where the experimental model is slightly shifted in the x and y positions. The difference between experimental and computational is very small, but slightly shifted. It's likely due to the positioning of where I tracked the spring using tracker, or very nominal things like air resistance that would change the time. So what's the difference between the period with y position and x position? The period in the x position is 1.64 seconds, while in the y position it's 1.55 seconds. We need to use the y period to calculate constants for the spring and subsequently its resting length, because the spring is being stretched in the y direction and being swung as a pendulum in the x direction. Using the x period would result in incorrect values because it does not, it has nothing to do with the spring itself. And the energy principle is satisfied because the graph shows that the change in energy remaining, the change in energy remains constant and displays that there is no energy lost. So in conclusion, we were able to calculate with high precision many inherent values of the spring and the oscillating system to compute and compare gravitational spring and potential energy, showing zero change in energy from any 2 points in the computational system. Thank you.